to our Science for Solutions session. I'm Tanya Birch, Program Manager on Google Earth Outreach. Today we've got 4 back-to-back examples of applications using Earth Engine for land cover and land use change, forest change, biodiversity. We'll also be featuring deep dives into Colombia and Brazil's forest and land use monitoring systems. Our speakers are Shijuan and Paulo from Boston University, Elkin from the Evaluation and Monitoring Program at the Humboldt Institute in Colombia, Rafael from the National Center of Geoenvironmental Information at MINAE in Costa Rica, and finally, Tasso Azevedo from MapBiomas. Welcome everyone to our virtual stage, and we'll kick things off with Shijuan and Paulo.
Hi, my name is Paulo Arévalo, and today, along with Shijuan Chen, we're going to present you 2 different applications of using CCDC on Google Earth Engine. CCDC stands for Continuous Change Detection and Classification. This is an algorithm that has been available since 2014, but it's been recently implemented on Google Earth Engine. And for that, we give special thanks to Noel Gorelick from Google and Yang from Oregon State University. So CCDC uses dense time series of remote sensing observations. Typically, this has been a Landsat observations, but we can really use this with any sensor, with data from any sensor. And what CCDC does is that it identifies change points and then models stable time segments between those change points. So an example of how that works is shown here. These are the time series, Landsat time series for 1 pixel, and this is the shortwave infrared, first shortwave infrared. What CCDC is doing is that it fits a harmonic model to these observations, and once the prediction is very different from the observed values, like it happens here in the year 2002 or 3, it flags a change, and then it starts again. It keeps doing that until the end of the time series, and in this case, it will look like this. What we're looking at here is a logging event in Louisiana in the United States, where we have stable forest until the year 2002. There's a logging event, and then forest regrows after that. Another example of this is shown here. This is a deforestation event in Rondônia, Brazil. There is a deforestation event around the year 2004, and then there's a conversion to agriculture. So one of the things we can do with CCDC is that instead of running this just for 1 pixel, we can run this for an entire study area. And one of the advantages of doing that is that we can get things like this. We can get a map, a layer that shows when the largest break or the largest change happened. The time series that you see here are pointed by the white arrow. That's representing an early change. Later changes are shown in red, and those correspond to the deforestation frontier. You can also get things like this. You can extract coefficients from the time segments, like the amplitude, which corresponds to the seasonality that you get in the segment. So agriculture is going to have a more marked seasonality than, let's say, forest, which in this case appears darker and it has lower amplitude. Then finally, you can look at things like the root mean square error of the fit of the model. So models that fit better and tighter, like stable forests, are going to have a lower RMSE value, in this case, a darker color. And agricultural lands are going to have a little more noise, and they're going to look a little more noisy with a higher root mean square error.
So using those CCDC coefficients, we can do land cover classification. And here is an example. To classify the land cover of this pixel, we first feed CCDC model to all available Landsat data of this pixel. And then we collect training data for different land cover classes. And then using those training data, we can train CCDC coefficients. And then we use random forest classifier to classify these segments. The first segment will be classified as forest. There was a fire in 2008. After the fire, the land cover became shrub. So the second segment will be classified as shrub. After another disturbance, the land cover became grass. So the third segment will be classified as grass. And this example shows how to classify land cover using CCDC. And also, we can use this method to monitor land cover change, such as deforestation. So what about monitor more subtle changes happened within a land cover class, such as forest degradation? Here, I'm going to show a research that we just published in Remote Sensing of Environment about monitoring forest degradation in the country of Georgia. Georgia is rich in forest, and it is a biodiversity hotspot. During the last 30 years, Georgia has experienced significant socio-economical changes, which put huge pressure on forests due to illegal logging for fuelwood and lumber. However, monitoring forest degradation is challenging. First, forest degradation are usually subtle disturbances, and it can either be an event or a process which complicates the monitoring. The objective of this research is to develop a method to monitor forest degradation and quantifying forest degradation in Georgia. There are two types of forest degradation. One is abrupt forest degradation, and here is an example. If we take a look at the time series of fraction of soil, there's a sudden increase in 2008. This indicates a logging event in 2008. Abrupt degradation is usually caused by logging events. To monitor abrupt degradation, we combined CCDC with spectral mixture analysis. Basically, we use fraction of end members and NDFI, which stands for Normalized Difference Fraction Index, as the inputs for the CCDC function. And then we use change magnitude of the breaks to monitor abrupt forest degradation. Another type of forest degradation is gradual forest degradation, and here is an example. Again, if we look at the fraction of soil in the time series, there's a gradual increase of fraction of soil from 2006 to 2019, which indicates a gradual decrease of canopy cover. We can also see this decrease of tree density from the high resolution images. Gradual forest degradation is usually caused by continuous illegal logging process. And CCDC SMA monitors both abrupt and gradual degradation. The slope of the fraction of soil was used to monitor gradual degradation. Here are some results. This figure shows the first year of forest degradation. The two inserts on the top shows forest expansion from more accessible areas to less accessible areas. The results shows that we can detect forest degradation accurately. The producers and users accuracy was 83% and 69%. The margin of error of forest degradation class was 16%, which is good. From this project, we learned that using CCDC on GEE is much easier than using CCDC locally. For this project, I run CCDC function for the whole country by myself. And for this project, the computational time of running CCDC is manageable. But the running time largely depends on what to export. If you want to export the intermediate results for every steps, it's going to take several days to get the final results for the country of Georgia. But if you only export the final results, it only takes several hours to get the results for the country.
Right. So this was a great example of how we use CCDC on a more local scale, and by local I mean a country scale. But we're also part of a project, the GLANCE project, which stands for Global Land Cover Mapping and Estimation. And as you can see, this is a global project where we aim at providing land cover and land cover change maps at annual time steps for the last 2 decades using Landsat data. And so what we want to do with this project is to provide a globally consistent, but also locally relevant maps. And we want to characterize the change and the trends that we see in our results. So these results are very preliminary. This is a global map of land cover for 2010. And what you're seeing here are 3 different scenarios in 3 different places of the world. On the left side of this image, you see deforestation happening in Brazil, the typical pattern of forest loss that happens along the ways, and then it extends to the sides. On the upper figure, you see the development of housing in Florida and also the construction of a new terminal for the airport. You see that in the red and dark colors. And on the right side of this image, you see the expansion of the water level for a dam in China, where the whole water level was increased, and that ended up flooding a lot of other areas towards the north. So These are the kind of things that we're aiming at for this project, characterizing the changes that we see at a global scale, but in ways that are also locally relevant. And so finally, for this work, for this analysis at the global and local scale, we developed a series of applications and functional libraries that help people look at the time series for single pixels, to process their CCDC results for larger scales, to look at the timing of change, to look at coefficients, and for CCDCMA to run CCDCMA, I'll also visualize the corresponding outputs of that. So if you're curious and want to see more of these resources and try them yourself, you can head to any of these links, look at the research we've done, the papers we published, and also look at the Google Engine code. So with that, we'll be happy to take any questions if there's any space for that, and you can feel free to contact us at any time. Thank you.
Hello, my name is Elkin Noguera from the Humboldt Institute. I'm going to explain about the Biomodels. The world requires tools to monitoring the biodiversity and to know how the biodiversity is being used. In Colombia, the Institute Humboldt generates the necessary knowledge to assess the state of biodiversity and to make sustainable decisions about it. In this context, Colombia, like other countries, requires multi-scale habitat maps of distribution to impact and conserve nature. Biomodels is a digital tool that allows communication between experts and biodiversity for the develop of maps of distribution of the existing species in a collaborative and open way. Therefore, this project goal was to obtain multi-scale habitat models using Google Earth Engine and ecological niche model methodologies. To achieve this goal, the project was granted by the Group of Earth Observations, GEO, and Google Earth Engine, looking for improving our planet with open Earth data. Biomodels is based on ecological niche modeling techniques. It integrates occurrence points from file explorations processed with living science and big databases, GBIF, Birch, Colombia, from collections and citizen science. We are using 6,000 camera traps, and 6 million of records available in GBIF and other databases. This data is related with algorithms and remote sensed data using Google Earth Engine to calculate maps of distribution of birds and mammals. We have two approaches. The first, a local level using data for camera traps to describe the habitat of the species, and second level or regional level using primary biodiversity data to describe the geographic distribution of the species. The integration of data and techniques is implemented in Google Earth Engine. We are running 4 machine learning algorithms, supporting vector machines, maxing from Phillips, random forest in Boston regression trees, through the coded editor in Google Earth Engine. The sensing remote data corresponds to modest data. For example, the normalized differential vegetation index in a DEM, digital elevation model, which allowed us to calculate maps of distribution of birds in a multi-temporal framework from 1,000 years to 2020 years at 250 meters of pixel. Currently, we have species distribution maps for 1,534 species of birds. This is regionalized models, and 38 species of mammals using camera traps, local models. This graphic corresponded to the trend in the distribution of a hummingbird sparkling violet and represents how the habitat changes over 21 years, with high values of rain available in raining years and lower values of rain in dry years, which are agreed with Enson oscillation. We consider that this type of maps shows a realistic trend of the species because the relationship between the birds and the healthy vegetation. This is a video how the models are implemented and how is the trends of the distribution of this bird. We are looking at the chains of the maps of distribution. This corresponds to 21 years. Yeah. This is the team. This initiative is in order to bring research, government, institutions, NGOs, and citizens tools and accurate maps of the distribution of the species in Colombia and other countries that serves as reference for studies and decision making in the biodiversity. Thank you to Geo, EO Data Science, Ecopetrol, Birch, and GBIF.
Hello, and thank you for the invitation to participate in the Geo for Good Summit 2021. It's a pleasure to be with you today presenting about how Costa Rica is using science for solutions. My name is Rafael Monge. I'm an economist, and I work as director of the National Center of Geoenvironmental Information at the Ministry of Environment and Energy of Costa Rica. If by the end of this presentation you wish to know more or continue the conversation, please contact me using my social media handle, Rafael Monge CR. 2021 is a very special year for us Costa Ricans. We are celebrating 200 years of our independence. Of course, we would have preferred to celebrate it without a global pandemic. However, this has made us feel very proud. Costa Rica has built a world-renowned green country brand focused on conservation, reforestation, and our system of national parks and protected wildlife. This has been an important driver of economic growth and well-being for Costa Ricans. Currently, 60% of our territory is covered by forests, and since 2013, the land use sector came to be considered a carbon sink in the accounting of our greenhouse gas emissions, absorbing up to almost 5 million tons of CO2 in 2014. We also face significant challenges in terms of sustainability. Deforestation in Costa Rica amounts to 17,000 hectares per year and occurs in a dispersed manner in relatively small territories, making its precise estimation a challenge. In addition, it is feared that this may have increased due to the effects of the pandemic and the need for resources, especially in rural areas. To face these challenges, we started working on a project with the objective to tackle deforestation and forest degradation using Google Earth Engine. This project is one of the 32 selected as part of the group of Earth observations and Google Earth Engine program that provides funding to tackle environmental and social challenges using Earth data. In the framework of this project, we have integrated the governmental and academic institutions, as well as international agencies that have the mandate and or that have specialized their work to face these challenges. In these photos of two of our meetings, of course, they're virtual for the pandemic. You can see represented people from our political authorities in the Ministry of Environment and Energy, colleagues from the National System of Conservation Areas, the National Forest Fund, the National Meteorological Institute, the Sectoral Planification Secretariat, the Environmental Administrative Court, the National Institute of Geography. This is from the government side. Also from the National University, the University of Costa Rica, PRIA's Laboratory, and CATI, and also agencies like FAO, Silva Carbon, and UNDP. You can even see our colleagues from EO Data Science, an organization that is supporting this program. And even Noel Gorlick from the Google Earth Engine team is there. He is the most colorful guy in the top picture. And this level of integration is very important, and it's very important to highlight as a baseline of this project. This has been achieved thanks to the development of our national land use, land cover, and ecosystems monitoring system we call CIMOCUTE. CIMOCUTE is a comprehensive national scale monitoring system that produces consistent information on the current extent and changes of forested, agricultural, and other land uses, land covers, and ecosystems. Several subsystems harmoniously integrate field and remotely sensed data to produce information that will inform decision-making and support the development and implementation of sound land management policies. This is conceptualized as an integrated system of systems founded on three interrelated processes: classification, that responds to the question of what; mapping, related to the question of where; and inventory and related registries that tell us how much. The classification process provides common land use, land cover, and ecosystem classification systems that are used by all the subsystems of the inventory and mapping processes. The subsystems interrelate synergistically to increase the value of the data. Simokute has been constructed as a highly participatory fashion that included stakeholders from more than 40 government, academic, international, and other institutions, primarily representing the environment, urban, and agricultural sectors. The work is coordinated through thematic technical work groups, which focus on specific subsystems or other elements of Simokute and have an advisory role. Their main functions are to develop, review, and adjust methodologies, indicators, protocols, standards, and other tools for monitoring the landscape while ensuring continuous improvement. The Tackling Deforestation project has been incorporated to the mapping working table. Costa Rica initiated the design of Simokute in 2015 and formally adopted it through an executive decree signed by the President and Ministers of Environment, Agriculture, and Justice in 2021. We have been able to demonstrate good performance in the management of our forest emissions that can be tracked in our greenhouse gas inventories. This has enabled us to receive result-based payments, and the latest contributions announced last year that are shown in the screen amounts up to $120 million from the Green Climate Fund and the World Bank's Forest Carbon Partnership Facility. This schematic shows a step-by-step description of the measurement and monitoring approach applied for establishing the reference level and estimating emissions and emissions reductions during the monitoring reporting period, presented in the monitoring report to the Forest Carbon Partnership Facility. And well, this report is currently under validation, but here is to show a little bit about the methodology for calculating deforestation and degradation. For calculating deforestation or loss and gain on forests, this is based on the cartographic comparison of wall-to-wall maps, resulting from the supervised classification of Landsat images. Degradation is measured by evaluation of the plots from a point grid with high resolution imagery. The degradation analysis was performed by plot sampling over a systematic grid of points performed only on the forest area remaining as such according to the land cover and land use map. This systematic grid was developed in the framework of the sample-based area estimation working group of Simokute and contains 10,242 points systematically distributed in our territory. That's for the level 1 of the grid. This work is our baseline. And with the project of Tackling Deforestation, we're looking for ways on how we can improve this analysis using new technologies, data, and tools like Google Earth Engine. This is the case of the new map of forest and agriculture that our colleagues from the National System of Conservation Areas is producing in coordination with the Ministry of Agriculture, the Ministry of Housing, and the support of the National University and the University of Costa Rica. Before this, SINAC produced this map that is in the screen. This is the type of forest map that was produced in parallel to the development of the National Forest Inventory. This map was created using 152 scenes from rapid eye sensor imagery acquired from 2012 and 2013. Each image was analyzed and processed individually and stitched together into a mosaic. The process took about 14 months. For the new map, SINAC wanted to overcome several challenges like budgetary constraints to acquire paid imagery the time spent in the production of the map in order to make information relevant with a 2-year basis, the need to depend on more from the participation of personnel from the government institutions and less from consultants. And also they wanted to develop a map that accounts for other land cover, land uses types, and not only forested areas. So they designed a map of forest and agricultural areas for 2022 that has been designed to use more readily available, frequently acquired free imagery with the whole process from acquiring the imagery to creating the GIS layers taking no more than 6 months or less, and carrying out the data processing stage mostly by institutional personnel. The process starts with the visual interpretation of high-resolution images of planet-based maps imagery on the Simokute point grid. The Sentinel-2 sensor data available in the Google Earth Engine platform is used for the classification. The classes were defined from the refinement of Simokute's classification system in coordination with experts from the urban and agricultural sectors. B2, B3, B4, and B8 bands were used, as well as the EBI, NDVI, and NDWI indices with a pixel size of 10 by 10 meters, where the random forest classifier was applied to obtain the land use and land cover map according to the classes detailed in the training. This has been done in a record time. We're currently revising the interpretation of points for the training, improving the cloud mask and incorporating new vegetation indexes to the analysis. Also, we are improving the capture of more points for certain classes that present some confusion to improve the accuracy of the map. This project has been executed and coordinated between the University of Costa Rica, the National University, and the National System of Conservation Areas, SINAC. The results of this project will be delivered by the first trimester of next year, and this exercise is planned to be executed every 2 years. And it is expected that this project will provide the science and policy interface of will improve the science and policy interface of Costa Rica by facilitating tracked land cover, land use changes over time, monitor the effects of conservation policies like biological corridors, rehabilitation of forests, mangroves, and other land covers, to estimate the challenges in the patterns of urban agricultural lands and keep track of our performance related to our sustainability goals like the SDGs, the National Decarbonization Plan, and other global and domestic policy targets. Well, rapid improvements in spatial data and computation present new opportunities for predicting biodiversity at different levels and understanding the relationship between biodiversity and its benefits to people. Costa Rica is making strides in the use of geospatial information to enhance conservation policies and promote a sustainable and resilient development for everyone by increasing agricultural productivity and sustainability, adding value to our tourism sector, and improving the land use management, and generating the conditions to better adapt our cities and ecosystems to climate change. Before I finalize, I want to thank you. I want to thank Google and every person and stakeholder that is helping us achieve these goals. Thanks for helping us create a better present for everyone. Muchas gracias and pura vida.
Hi, so we have this situation in Brazil where 75% of our greenhouse gas emissions comes from land use and the land use change sectors. So it's very, very important that we understand how the land is changing, the use of land is changing over the time. Not just deforestation, but also what happens afterwards and what kind of transformations are happening. So that's what is the initiative of MapBiomas. It's a coalition of various organizations involving startups and NGOs and universities to build up this time series to understand the land use change in Brazil. So it brings together different types of mapping, the land use, land cover change. Also, there is specific initiatives on water, fire, and also on deforestation specifically. So I will talk a little bit about how we do the mapping for the land use change over the time. So we are working with a time series that on the last collection goes from 85 to 2020, having annual maps with 25 land cover classes. So to do so, we have this basic structure where we use the historical data from Landsat, processing pixel by pixel at Google Earth Engine using machine learning, and this allows us to work on a collaborative way. So every organization on the network, it's operating on the same space inside Google Earth Engine, so we can exchange our codes and also exchange the use of the space and the assets that we produce for the project. And so the way we organize ourselves is that different groups in the network work on different biomes or ecosystems in Brazil, like the Amazon, the Cerrados, and each one of those biomes. And then we have groups working on topics that covers the whole country, like pasture, agriculture, the coastal zone, and urban areas. So the steps we do is that first we work doing our mosaics. Then, so we do the classification of each one of the classes that we want to map separate. So we use different classification methods for each one of the classes. So we use, for some of them, we use random forest. For some of them, we use UNet. So we work in a way that we evolve the classes that we are mapping over the years in different collections. So we start at the beginning of the project in 2015, trying to map just 7 classes for 8 years. And then as we go year by year, we are increasing the number of classes that we are mapping. So we are learning to classify each one of those classes. And so the maps are getting more detailed, more updated with newer information, and also with a larger time span. And so we are now on collection 6 that goes for 25 classes over 36 years. That's the accuracy. We analyze the accuracy of the maps, not just the whole accuracy for the whole country, but also for each one of the regions, the biomes, as we say. And also we have the accuracy for each one of the classes that we are mapping. That's very important to help the users to understand where they need to, to be more cautious when considering the data that we are providing to them. All of that goes to a platform, which is it's open online where anyone can navigate over those maps and classifications. This allows us to see the information both in time and space on different types of organizations. So in this case, for example, we are seeing the data for the state of Mato Grosso, and you see the map in 85, and you can navigate, let's say, for 2000, and then for 2020, and you see like a lot of transformation from forest to other classes of use over the time. And everything you see here, you can also see obviously the statistics on area over the time. The platform also allow for see this on for every municipality, for example, for every protected area, conservation unit, and all of that is pre-processed using Earth Engine, creating different assets that allows for quick access when we are looking at the platform. So this is one municipality. See, for example, in 85, just one of the 5,000 municipalities, and then you can see 2020, but also you can see all the transitions, the changes that are happening over the time. So you choose a pair of years. Let's say here in this case, I'm seeing 85 and 2020, and you will see in red everything that lost natural environments, for example. And then you can also see that in a Sankey diagram, so you can see from what to what, the different classes, what are the changes that are happening in various levels of details in terms of the classes that you are seeing. Also can see it in a table and so on. Also, we are using some interesting possibility that comes with Google Earth Engine. One of them is to tell the story of the pixel. So you click on any place on the map, and then you can see the classification of that pixel in every one of the years of the collection. And this is done on the fly on the platform. And the other one interesting is this timeline, or that you can select any area of the map, and it will build up a time lapse of that specific area. This is also done on the fly in the platform using Earth Engine. There is several other maps that is being produced, like deforestation, regeneration, maps of irrigation, infrastructure, and so on. That it's just maps that derive from the original map of land use and land classes. So the other thing that we are using is we create a kind of a toolkit in which you can use to download the maps and the statistics of any place in Brazil, considering all those maps. So this is available throughout for any one of the collections that we have, and then you can select any part of the territory, and download the maps for the year that you select, and also it comes together with the statistics of each class on the maps that you asked to download. Also, all the codes are available on GitHub, so other people can reproduce any step of the process that we make to produce those maps. I'm just talk very quickly about another initiative that we are doing now using planet imagery, which is much more detailed, and it's a different challenge of work. So since the 80s, we have in Brazil tons of systems that are detecting deforestation in different levels. And the idea is to detect as close as real times for allow for the action against the deforestation. So, but we identify a problem, which is a very little quantity of those deforestation alerts have actually transformed into action in the field. So we bring together the institutions that are producing alerts, like Amazon, like INPE, the Spatial Agency in Brazil, GLAD, from University of Maryland, and others, and also with the users of those alerts in the country. And we find out that in order to increase the efficiency and efficacy of using those alerts, we need to produce alerts that will be covering all the biomes in Brazil using the same approach, validated in high resolution, which makes much easier to convince the judge and anyone during the process that this is a real deforestation. And also something that would be published on one single platform that could be customizable for the user, so they can act more quickly. So what we are doing on MapBiomas is taking every single deforestation alert that are happening in Brazil, one by one, and we are getting them into a platform with Planet, where we select an image before and after deforestation on the, just go to every single daily image. And then we send this to Earth Engine. And in Earth Engine, we redesign the deforestation based on those high resolution imagery. So you have this sign of deforestation coming in, and at the end, what you have is a perfect design of what is the deforestation with an image before and after. So it's very clear to understand what happened. And you have precisely definition in space and time when deforestation happens. Then we cross all this information with the data banks of protected areas, authorizations, penalties, and so on. And we can produce a specific report for each one of the deforestations that are happening in the country. So this goes to a platform where you can navigate to each one of those deforestation alerts. And for each one of them, you have this image before and after, and you have reports for each one of those deforestations, or each one of the properties that these deforestations are crossing in. And so this is available in different formats, like a PDF reports, or shape files, database, and so on. There are a lot of plugins to connect to that. And this allows for really interesting evolution. Like in 2018, we had 150,000 deforestation alerts produced by the different systems in Brazil, and only about 1,000 actionable reports prepared by the federal government during the whole year. And since January 2019, when we start to operate this MapBiomas alert, we have reviewed 400,000 deforestation alerts and produced 165,000 action reports. And we are now producing about 1,100 per week, which is like more than what is being done in the whole year of 2018. So this results that we have today 1,500 registered users, which are specific users of the reports that are prepared, which includes 158 institutions, and 69 of those, they produce customized reports. So they produce their own reports based on the information that that is being provided. So it's I think it's a very action-oriented use of the the potential of Google Earth Engine and the the new sensors like that it's worth to share with all of you. That's it.
Thank you, Tasso, and thank you to all our speakers in this session. We've heard how Boston University is producing land cover change and forest degradation data using the CCDC algorithm, how Biomodels is preserving biodiversity in Colombia, how Costa Rica is measuring carbon emissions, reducing deforestation and degradation with the Simukute platform. And we've also learned how MapBiomas monitors landscapes and deforestation in Brazil. We hope you've been inspired by these applications, bringing the latest science into solutions for a nature-positive future. Thank you for joining.